Hi everybody, this is Mrs. Ellsworth. What we're going to be talking about today is work and energy, and the physicist's definition of work and energy. We're first going to tackle work, okay? Work is any type of object or thing that you can move with a force that you apply to it, and it goes in the same exact direction of your force that you apply to it, and it moves a certain distance. So work is a capital W, and force is a capital F, of course, and then also times distance. If you're going to solve this instead for distance, here's a manipulation. D equals W over F. And if you're going to be solving for force, it would be W over D. Now, let's talk about some units here. We already know a few units. We know that distance or displacement is going to be in meters. We know that force will be in newtons. So we've got newtons times meters here. So work's unit will be newton meters. Okay, and work can also be joules. So this is also joules. Capital J. Okay. So what is work? It's being able to push an object in the direction of your force a certain distance. If you're pushing the object in this direction and it goes 90 degrees off, if you ever go and look at cosine of that, it's going to equal 0. So that is when there's no work done. If you're pushing this way, but something is bigger is pushing you that way, then it's going to be negative work. Okay, so something can go off to the side here. Okay, it's like here's the direction you're pushing and it's going off to the side some. And if that's the case, then we're just going to have to figure out how many degrees that is and use our vectors for that. Okay, so let's talk about a couple of other things. When is work being done? And so work is being done when the object is moving. So it has to move. Okay, if you are a weightlifter, okay, and you are lifting some of those barbells up there and you're holding it up here, or if you're going to hold it up above your head, I don't know if you actually do that or not, but if you're doing that and you've got the barbell up there while you are holding it there for 5 seconds or whatever that it is, when it's in a hold, then it is 0 work being done because it has to move. It has to go distance. If that distance is 0, then there will be no work done. It's that simple. Okay, so it has to move. So like if I went and asked somebody to come up here and move my whole desk system up here, just push on it, it wouldn't go anywhere. So then of course you'd have 0 work done. Okay, next thing's next. Energy is the ability to do work. So these things are related. There's 2 types of energy. I should probably write down that first definition that I said here. Energy is the ability to do work. Okay, and sometimes you'll see that's also the ability to cause change. And so you can look at it either way. Anyway, the potential energy is one of those types of energy, and potential energy is the energy an object has, due to its position or its shape. Okay, and we're going to talk a lot more about several of those. In fact, I wonder if on your sheet if I have these switched around. There is 2 different types of potential energy formulas, so I'm going to tackle that here in a little bit. But anyway, so let's go and talk about kinetic energy first before we do that. See, right here's one potential energy. There are actually 3. The first one is elastic potential energy. Okay, the second one that we're going to label here would be gravitational potential energy. And then the third one is chemical potential energy. Okay, now there's only one type of kinetic energy, okay, and it is kinetic energy, and it is talking about moving something. It's always in motion. If you're talking about anything that's in motion, it is talking about kinetic energy. Once it is stopped, or if it isn't, well, just once it's stopped, then it has no kinetic energy. Then it's all potential energy, perhaps. Anyway, so we've got 1/2 mv squared. Okay, and you know these already. This is the mass. This one right here must be in kilograms. All energy is measured in kilograms, even these ones that are up here later on. Okay, the velocity is measured in meters per second, and it must be in meters per second. Okay, and then kinetic energy is energy. Remember, energy is the ability to do work, so all energy is measured in joules. Okay, and so this right here will be in joules too. Okay, and so that works pretty nifty. Okay. Anyway, if you were going to solve this stuff for mass, okay, mass, then you'd have 2 times ke all over the velocity squared. If you were going to solve this for velocity, okay, anyway, so we've got a squared here, so I got to do some thinking here. I've got 2 times ke all over the mass, and then since this is going to be squared, I got to take the square root of it just to get velocity. Now you're going to be square rooting the whole fraction right here. Okay, you got to square root the whole thing. So calculate this stuff, divide by that, then once you calculate that, press enter, and then take your square root, enter again. Okay, so those are 2 ways of manipulating this. Okay, now elastic potential energy is talking about like a spring that is hanging down. Okay, we'll be doing a lab with this. Okay, and you've got a weight on it, and how far did it go down once you place that weight on there? Okay, so how far did it distort it? And I'm doing it from the center of the mass of this. So this distance right here is x. Okay, how far did it? And these must be measured in meters, of course. Okay, now some springs are really thin and really weak. Okay, so you could have had another spring on here. Okay, and then once you put that mass on it, then it really stretches out, doesn't it? Okay, so some of them have a really low spring constant because now this right here really stretched out. It's got much larger distance there that it went for some displacement. Anyway, this one right here is a much weaker spring, and so it's just really easy to pull it apart. This right here is a little bit more difficult. So this is the spring constant that represents that. So we write this formula is as EPE, okay, and it's 1/2 of the spring constant, and that constant is either assigned to it or else you have to figure out what it is, and that's K, because it's going to be a constant, this one. Okay, and it's times the bending, or in this case, this stretching. Okay, so it could be like even leaf springs too, you know. Anyway, and then so this right here is going to be x squared. Okay, so that's how you'd calculate that one. And I said you might have to also calculate the spring constant. So it'd be 2 times the EPE. Okay, and it's all over x squared. Okay, and then that's going to equal the K. Oops, I don't need a square root for that. Okay. 2 times EPE divided by x squared. Yeah, okay. So we've got that down. And then also, again, this spring constant's in a pretty nifty unit. Okay, it's going to be joules per meter squared. oh, I need to get a pen here. So K is always measured in joules per meter squared. Okay? Okay. Now, here's one of my favorite ones. Okay, if you've got something that's up on the top of a cliff, okay, if it's a little bitty pebble, yeah, it could still hurt you. Okay, here's you. Hi, Dilly. All over there. Okay, now if it's a big, huge rock, a boulder, oh my gosh. Okay, so the mass matters, and how high it is, of course, matters, and then also the gravity according to Earth. Okay, so we've got GPE equals mgh. Okay, we do not need to worry about this being positive or negative in this case right here, but really think about it. If you did it with if you did displacement, this would be a negative value, and this would be negative 9.8. So really, it just all washes out in this. You won't ever have a negative mass, of course. Anyways, so the mass is always measured in kilograms. Okay, and then gravity, of course, is meters per second squared, and then the height is in meters. Okay, so you could also solve for the height if you were given some gravitational potential energy. So height, oh, I'm sorry, I should also say this is in joules. Okay, so if you're looking for the height, then it's going to be the GPE divided by the mass times gravity. If you want to figure out the mass, then that would have to be over gravity times height. Okay? Okay, so how is this all connected? Well, there's a theorem that helps us with this, and that is the work energy theorem, and it's talking about, remember that the energy is the ability to do work. Well, that means that they're equal to each other. So when you're looking at something having lots of work, there's going to have lots of energy, at least potential energy or kinetic energy. Anyway, so if you go and you look at this type of situation here, I've got this pendulum. Okay, it's attached to the ceiling right here. Okay, and it's hanging down. The weight on a pendulum is always a bob. Okay, and so we pull it back, and it goes back and forth and back and forth. And you've heard me talk about how physics clubs in college makes you do this with a bowling ball, you know, and put your nose up to it, let it go, and let it go come across. And you should know that it's always going to lose some energy, because everything loses a little bit of potential energy, a little bit of kinetic energy because of friction. In this case, you could have some friction inside of your cord, you could have some air resistance, whatever that it is. It should never ever go past it unless you had somebody over here pushing, like somebody on a swing. You know, on a swing, you get less and less and less and less, and oh, boring, right? But the only way that you'd get it to go past here is if you added energy to it. Well, we're going to say in this case right here that we're going to pull back this bob, and we're going to hold it right here, and it's got 100% of potential energy while I'm holding it. Okay, and then notice that if it's going to be half the height, it would have half the potential energy. Well, where does the energy go? Where does it go? It just doesn't disappear. Well, it's because it's moving now. And so now it's got some kinetic energy. So it started out being zero kinetic energy, and now it's increasing, and halfway it's half and half. And then as you go right here, it's just about the fastest it will go right here. So that's 100% kinetic energy. And then now it's going to start slowing down, and you know the speed is connected to the kinetic energy, right? Speed is involved. Okay, and so now it's slowing down, so it's losing its kinetic energy because it's slowing down. And halfway through here, it's going to be 50-50 again. And then up here, right when it stops, it'll have zero kinetic energy, and it will have 100% potential energy when it stops. Now, you might be asking yourself, well, how can she say it's going to have 50-50 potential energy and 50-50 kinetic energy? Well, if you stop it right here, it will have 50%. And it still won't go quite as fast as if you were doing that otherwise. So you can kind of think of it as taking a snapshot of it right in the middle, and that you'd have 50-50. Now imagine that this bob is all done moving and it stops right here. When that's the case, you know it has no potential energy when it's not moving. It's at the bottom, has no potential energy.